So in the last lecture, we were talking about the Gibbs-Duhem relationship. Yeah. So let's recap a little bit about Gibbs-Duhem relationship, and then we'll move to the phase diagram today. Okay. So this Gibbs-Duhem relationship. Okay, Gibbs-Duhem relationship is the relationship between the partial property inside of the solution. Okay, so one of the primary, actually, the Gibbs-Duhem relationship is if you have the, so when the solution thermodynamic property y of solution is given by yi, xi, sum of this, and when this one is partial property, for example, so any kind of thermodynamic property of the solution can be sum of the partial thermodynamic property of the each species times the mole fraction of each species. Okay, so that actually gives you the total. When you have this kind of relationship, then when you do some derivation of the couple of the actual equation, eventually you get this one. So when I have xi 0, okay, and so for example, when you have xa dga plus xb dgb equal to 0. Okay, so for example, if this is the partial property is the Gibbs energy, partial Gibbs energy, then xa dga plus xb dgb equal to 0. So that is one of the actually the relationship we can actually define from the Gibbs-Duhem relationship. And the other one is when you have partial Gibbs energy of A equal to total Gibbs energy times mole fraction, so Ty Ty over dxa. So this is the, okay, yeah, this is the another relationship. So we have the two kinds of the Gibbs-Duhem relationship, Gibbs-Duhem equation. The one of them is this one. So sum of the mole fraction times of the d, for example, partial property of the component equal to 0. That's one of them. And the other one is if you know the total solution, so ya equal to y solution plus xb times the dy of the solution over the tx of the solution, txa of solution. So this is the other relationship we can derive from this actual relationship again. And so if you're actually using this, so if you're talking about the partial Gibbs energy, so this will be like a G of A, partial Gibbs energy of A equal to Gibbs energy of solution plus xb dg of solution divided by dx a mole fraction. So you can apply this one. So when you are using this equation here, above equation, if you know the partial property of the one of the component in the system, so if you assume this is binary system, if you know the partial property of the A component in the system with the composition, then you can make a derivative. Then you can actually get what is partial property of the B in the same system. Okay, so basically first equation can be applied when you know the partial property of one of the component completely. Then you actually can calculate the other partial property. Okay. Partial property of the other component. And second equation is, the second equation can be applied when you know the now total property. So when I know the total property of the solution, then partial property of that, actually the partial property of the component can be calculated from the total property. That's what it means. So GA equal to G solution like this, and GB equal to G solution times XA over the D solution over the DXB. Okay? Okay? So depending on the information you have, you can actually use either one of these solution, this relationship to calculate the partial property. Okay? One of the, when actually we are really using this kind of partial property or Gibbs-Duhem relationship, and there's the typically two cases if we look at most of the thermodynamics actually the relationship, thermodynamics actually the assessment, or thermodynamics actually measurement. People using actually Gibbs-Duhem relationship mostly for two kinds of cases. One is we are measuring the enthalpy of the mixing of the system, of the solution, for example. So let's assume we have liquid iron and the liquid manganese have a liquid solution. So we are mixing these two together, and we try to find out what's the enthalpy of mixing of the binary system, liquid phase, for example. So you can measure the enthalpy of mixing, total enthalpy of mixing, for example, sometimes. Okay? So basically, I have A and I have B. I mix it together, and then I measure how much heat is released or how much heat is necessary to maintain the same temperature. That's actually giving you what's the mixing enthalpy. Yeah? And then once you know all this mixing enthalpy of the entire solution with the composition, then based on that function, now you can calculate what's the partial enthalpy of mixing of A, partial enthalpy of mixing B. Okay, by using this relationship. Okay. Or sometimes people actually also measuring the enthalpy of mixing, not like total enthalpy of mixing. They are really measuring the partial enthalpy of mixing too. So how they are measuring is, they make a solution of manganese and iron 50-50%. Okay, and then they are adding very small amount of the iron inside of this solution and measure the heat change. This is definition. By definition, this is the partial enthalpy of mixing of A, the iron. Yeah. So with the composition, at the given composition, you do the experiment like this, one by one. Then you can measure partial enthalpy of mixing of A component in the solution, and then using this equation, you derive what's the partial enthalpy of the B in the solution. Both of them is possible. So enthalpy of mixing is one of the actually good example. And the other example is, we actually also can develop some technology to measure the Gibbs energy directly. Okay? And one of those the method is using the the kind of the electrical current. Okay? Well, it's actually theoretically it's voltage. Because Gibbs energy, in the electrochemistry, Gibbs energy can be converted to the electrical energy, especially the voltage. Okay? So probably when you, I don't know whether you have learned some corrosion or some electrochemistry already or not. So Gibbs energy is minus NFE. So it's N is, F is Faraday constant, and then E is electrical voltage. So Gibbs energy can be converted to the voltage. Okay? So people using some special equipment to measure the voltage for the given solution. Okay? Then they can measure actually the Gibbs energy over solution. So when you have an iron manganese binary system again, then you can measure depending on the composition, you can measure the Gibbs energy over the solution. Then by using this relationship, you can calculate what's the partial Gibbs energy of A and the B. Or if you measure also the partial Gibbs energy, then you can use that actually to back calculate what's the partial Gibbs energy of the other system. You know what? In the morning I left actually my window open in my home. terrible. Anyway, so this is actually typically when we are using this kind of thing. Now, actually, that's actually very special case. Sometimes people measuring the activity of the component in the solution phase. And there's different way to measure the activity. And people want to use this activity of the one component in the solution to calculate the other component activity in the solution by using the Gibbs-Duhem relationship. But when you're actually using those kinds of when you try to actually find the activity of the other component, you have to be very careful, because I will show you actually that specific example. So, partial property, but one of them is basically activity. Actually, it's related to the partial Gibbs energy. So if you look at it, XA, so let's assume this is AB binary system, binary solution, and XA DGA plus XB DGB should be 0, yeah? So that's the Gibbs-Duhem relationship. And then, yeah. So if you apply this one, this is XA D of GA. Derivative of this one yeah, and GA naught and GB naught is constant at the given temperature because it's independent of the composition. So derivative of this one, this is 0 basically. So this will be XA and D ln AA plus XB D ln AB equal to 0 eventually, because and then you basically divide the RT in the both sides, so then you can get this one. Yeah, so is it okay? So this means if I know the activity of A, depending on the composition, then I can calculate activity of B in the system, in the given solution. Okay? However, if you just try to actually apply this one directly, it's very, very difficult. So so activity of A is basically like this. Is it okay? You get it? Plus is it okay? So I'm just dissociate activity equal to activity coefficient times mole fraction. So then you can get this relationship equal to 0. And then this XA D ln XA, XA D ln XA is 1. XA D ln XA is 1. So XI D ln XI equal to XI, yeah, so it's a DXI, yeah. So if you apply that, this is XA D ln gamma A plus XB D ln gamma B plus DXA of course this is 0 because it's cancelled out. DXA plus DXB equal to 0, yeah? DXA is minus DXB. XA plus XB equal to 1. So change of the XA is the minus of the change of XB. So it's cancelling out. So basically we have this relationship. There's the two actually, so this one or this one. We have to use one of these to calculate the activity. If I use this one, from the one of the activity, I can calculate the other activity. If I use this one, from the one of the activity coefficient, I can calculate the other activity coefficient. Yeah. And if you know the activity coefficient, activity is very simple. Yeah. Which activity is activity coefficient times mole fraction. So you can get it. So, and in reality, people using this one, then this one. So I'll show you why we are not using this one, then, and we are not using this one, and instead of that, why we are using this one. So it's a problem. So, if you're using the first relationship, XA, if you're using this one, basically T ln A equal to minus it like this. So let's do the integral in the both side. Okay, and you can do it like XA. So XA equal to 1 to XA equal to certain XA. Is it okay? Because XA equal to from 0, then this becomes 0. So it's very difficult to actually calculate. So at least let's just start from XA equal to 1 to XA. So XA equal to 1 to certain XA. Okay? Then, okay, so this one, so it's ln AA from XA to the XA and XA equal to 1. And this means XA, when XA equal to 1, activity of A equal to 0. It's 1, so this term is 0, yeah? So this is same as ln AA at XA, so at XA. XA equal to XA. Okay? So this is okay. Equal this part. So this part is actually the difficult. So this one, so XA over XB over XA, ln AB. But when you look at it, when XA equal to 1, activity of B. So basically, if I plot this one, so this part, now it will be like this. So let's take, okay, this is dy. So this is XA of XB. Yeah, so this is XB of XA. And then let's take this one. No, it's not. Sorry. So this is eventually this one. Yeah. So let's take this one, XB. Ln AB, D ln AB. So XA, XB, D ln AB. So integral dx. X integral of some function. So when you say integral of some function, so if this is the, so let me see, y equal to integral fx dx, then this will be eventually y equal to, so whenever you have this is fx, so this is x, and then this is function of fx, and this is sum of actually your total, yeah? Am I right? So this is the thing we want to actually calculate, yeah? So this is y eventually. Yeah, if you have a function like this. So if I now write this one, so this is my function inside xb of xa, x, so this should be d, sorry, this is ln a of b, yeah, and this is xb of xa minus, for example. Or I can say this is minus and this is plus, the same thing. Is it okay? So this integral of this part is like this one, and then we have to basically find the area here. That should corresponding to this value. Am I right? Is it okay? Mathematically, is it okay? However, if you look at this one, when xa equal to 1, so when xa equal to 1, so it means when xa equal to 1, xb is 0, so basically at 0 point here for the y-axis, the ln ab, activity of b, when xa equal to 1 is 0, yeah? Because there's no b at all, so xb equal to 0. So ln 0 is minus infinity. So this one is plus infinity, yeah? When it's 0. So this curve is go forever. So you are actually sum, but you cannot sum because you have infinity value here. Is it okay? So this is mathematical, you cannot solve this problem. Okay? So mathematically, so I know what I want to calculate, but unfortunately, if you actually plot your x activity of b, so I'm assuming that I know the activity of b with the composition. However, because of this kind of the infinity problem, you cannot solve actually the activity of a. Is it okay? So you cannot use this one. However, if you are using the other concept, so we try just this one, but if you are using this one, you can actually solve the problem. So a, d ln gamma a. So it's exactly the same, actually, the relationship, but instead of using activity, we are using activity coefficient, okay? And in this case, so now d ln gamma a equal to minus okay? And then let's make integral again. We are doing this one. This is d ln gamma a, and when xa equal to 1, gamma a equal to 1, because it's Raoult's law, so it will be 0. So gamma a when xa equal to xa equal to minus integral xb of xa d ln gamma b xa equal to 1 to xa. Okay. Now, if I plot this one again in the graphic form like this, then it will be like this. So this is xb over xa, and this is minus t minus ln gamma b. Okay. When this is 0. So when xa equal to 1, at that condition, ln gamma b is, so when b become 0, when b become very small amount, the activity coefficient of b have to follow Henry's law. So activity coefficient, there's certain value existing. When it's 0, but however, when it's infinitely small, close to 0, there's still some number, yeah? It's not 0. There's some Henleyan active coefficient. So this will be minus ln gamma b naught basically at 0. All right? That's Henry's law. And then you have some kind of function, whatever it is. And so basically, when xa equal to 1 to xa, so this will be from 0 to some value. So you're basically summing this value. Summing this value to calculate your Henleyan active coefficient. Is it not like this? Is it not like this? It's like this, because this is x-axis. So this one. So mathematically, it's possible to calculate. I mean, the best way is you just plot it with the composition. So plot your Henleyan active coefficient or activity coefficient of the B with the composition, and then just summating all this area. That will give you at least what's the activity coefficient of A. And once you know the activity coefficient of A at the given composition by using this relationship, then you multiply this one, get the activity of A. Okay? Okay, good? So most of the time we can apply directly the Gibbs-Duhem relationship, but when you're actually talking about activity or partial Gibbs energy, you have to do this way, because otherwise you'll have the mathematical actual problem to calculate. Okay? And actually, a lot of people who is doing the thermodynamic using this relationship. As I mentioned, there's the two most common thermodynamic property people actually using. People like try to use the Gibbs-Duhem relationship to find out the partial property, and one of them is enthalpy of solution, enthalpy of mixing, and the other one is Gibbs energy of solution or Gibbs energy of mixing. So from that we can calculate partial Gibbs energy. So if I know the Gibbs energy of activity, then we can calculate partial Gibbs energy. Yeah? Okay? And now let's try to use this Gibbs-Duhem relationship for regular solution. So when you have regular solution, G of solution equal to GA XA plus GB XB. So it's a partial thermodynamic B, and partial thermodynamic property is GA naught and this one is do you remember this one? So this is basically the Gibbs energy solution for the general Gibbs energy solution expression for the general solution. So Gibbs energy solution is mixing or the sum of the partial Gibbs energy for each component, and partial Gibbs energy is Gibbs energy pure plus RT ln activity, and activity is activity coefficient times mole fraction. So eventually you will have ended up this relationship, yeah. And when this is a regular solution, we say that this GXS is expressed omega XA XB. Okay? And also this omega is constant term. It's not independent of temperature. So this is actually GXS means HXS minus TXS. entropy. So G equal to H minus Ts, but this is 0 for the regular solution, because regular solution, the excess parameter is only contributed from the enthalpy of mixing. So interaction term is constant. So this one, you need a temperature dependence term. So this term should be corresponding to the only enthalpy part of the solution. And this enthalpy, sometimes we call it like this one. Sometimes people using this one, excess of mixing. And so this is delta. So delta G excess of melting, delta excess of mixing, T delta S excess of mixing. All this one is based, just different terminology, but it's same concept. So this one is corresponding to for the regular solution. Is it okay? Because this is extra mixing term. When you have the mixing, there's the extra term. That's excess term, but you can even say that this is delta of mixing term, extra mixing term. Yeah. Is it okay? Everyone following? So now, let's look at this one. So, do you remember that? We say that, okay, when it's regular solution, so this H is corresponding to this one. And then I say that, okay, partial enthalpy of mixing of A can be calculated from this term. Okay, so let's look back this one, GXS. So GXS is corresponding to this one, first of all, RT, ln. So this is same as this one, and this is same as this one. All this one is same. Is it okay? And then, so this delta H of mixing should be expressed by this way too. XA delta H of A of mixing, excess mixing, plus XB over delta H of excess of B of mixing. So enthalpy of mixing, or partial enthalpy of A mixing, partial enthalpy of mixing of B corresponding to the total enthalpy of mixing too, yeah? Very good. And then, now let's go back to this term, very first term here. If you look at very first term, okay, this is XA multiplied with something, XB multiplied with something here. So if I just rewrite this one, this will be XA, RT, ln gamma A, plus XB, ln gamma B. If you just compare these two, certainly delta H of A mixing, excess mixing or A mixing for regular solution should be RT ln gamma A, and then we can get this relationship very quickly by just comparing these two equations. Yeah? Okay. And then now, if I use the Gibbs-Duhem relationship, okay, so delta H of excess mixing is omega XA XB. Okay, so what I want to do is I want to know the partial enthalpy of mixing of A equal to total enthalpy of mixing plus so this relationship. I want to use this relationship to get what's the partial enthalpy of mixing. So delta A of mixing equal to total. So omega plus is it okay? So XA, XB, so XA times 1 minus XA. So I just changed the XB to the 1 minus XA to get the actual derivative inside here. So then this will be omega XA, XB plus XB. And then this term, first term is omega. Second term is minus 2 omega XA. Okay? Then this will be this one minus 2 times of XA, XB. So this will be basically omega XB minus omega XA, XB. And this one omega XB 1 minus XA omega XB square. So this one same as this one. And this one is same as, from here, this one is RT ln gamma A. So we have this relationship. But when I actually explain the regular solution, when you do the exercise, homework exercise, I say that RT ln gamma, so when you have the regular solution, if you know the regular solution parameter, then RT ln gamma A equal to omega XB square, RT ln gamma B equal to omega XA square, yeah? Regular solution parameter times mole fraction of the other one square. And this is actually derived from this Gibbs-Duhem relationship. Is it okay? You good? Personally, I don't like regular solution very much, but it's a very good example for the exam. It's very easy to actually apply in the exam. You good? So that's the whole relationship. So whenever actually you have problem to solve something in solution, you always have to start in this way. And then you have to derive further and further, and then you have to try to add some special actual condition in the last actual stage here. Then you're not going to make any mistake. You have to always start in this way. Okay, any question? So we finished the solution thermodynamics. So in the first 1 month we finished the first law of thermodynamics, second law of thermodynamics, and third law of thermodynamics. I hope you still remember that. What's the third law of the thermodynamics? Sujang, what's the third law of thermodynamics? You can speak in Korean. What's the third law of thermodynamics then? Okay, that's the third law of thermodynamics, yeah? And think about how to explain that to your grandmother. Okay? Or my grandmother, my mother, if you like. My grandmother passed away last year, so. And then, so we learned actually basically all this thermodynamic law, and then we derived the equation how to, we eventually, even though we had first law, second law, and third law of thermodynamics, that is not enough to actually apply in the material thermodynamics. So we derived actually new equation called Gibbs relation, Gibbs energy equation, yeah. And so Gibbs energy was H minus Ts. And the reason why we derive the Gibbs energy is we don't want to take care of all the surrounding of the system, because, we are just focusing on our own system, and in order to actually tell whether our system is in equilibrium state or not, we have to find some new relationship than the second law of thermodynamics. And by the way, second law of thermodynamics is whenever you have spontaneous reaction, your entropy of universe is keep increasing. That's the second law of thermodynamics. So according to the second law of thermodynamics, when you are in the equilibrium state, your entropy is not increasing anymore. So the entropy of universe equal to 0. That's the second law of thermodynamics. That's the equilibrium state according to the second law of thermodynamics. However, for the second law of thermodynamics, we have to consider both system and the surrounding. So it's not applicable very well for the real world. That's why we derive this Gibbs energy function, which is only take care of the inside of system. And so now, by using the Gibbs energy equation, we can now tell whether my system is in the equilibrium state or my system is going forward or backward, depending on the Gibbs energy actual value. Okay? So thermodynamically, any kind of system want to be more stable state or more equilibrium state by decreasing of Gibbs energy. So when your Gibbs energy is decreasing direction, then it means you are going to the more equilibrium stage. So it means the reaction is going forward to that actually the equilibrium stage. Okay? So when delta G of, especially chemical reaction, when delta G of reaction is negative, then it's forward reaction. When delta G become eventually 0, then you are in the equilibrium state. Yeah. And we learned all this the chemical reaction after that, considering only gas phase. Gas is the only solution. When gas is the solution, the Gibbs energy, partial Gibbs energy of gas phase was expressed by Gibbs energy of gas species at 1 atm condition, pure Gibbs energy of the A species of gas at the 1 atm condition, plus RT ln partial pressure of the gas species in the given system. Okay? And the partial pressure is mole fraction times total pressure. So the gas actually, the thermodynamic partial Gibbs energy of gas species is depending on not only just mole fraction of the species, it also depending on the total pressure of the system. Yeah? And then we try to use the similar kind of concept to the solid or liquid solution. So the first thing we have to derive was the concept for the activity. Okay? Because at least we know the gas phase very well. So we try to develop some new relationship to find out what's the partial Gibbs energy of the species in the solid or liquid solution. We try to make a virtual experiment between the solid or liquid solution with the gas phase. Because gas, we know very well. We know the ideal gas law and then partial Gibbs energy of gas species very well. So by using those relationships, we derived actually the activity concept. So activity, the theoretical, original actual concept for the activity is activity of the component I in the solution is partial pressure of I, which actually equivalent with that actually given solution, divided by partial pressure of I when the solution is only I, only contain I at the given temperature. Okay? So that partial pressure difference between the reference state and between the real state and the reference state, that actually gives the activity definition. Okay? And then activity is given by the activity coefficient times the mole fraction, because this is just very artificial definition, because we want to actually define the activity as a function of composition. So in order to do that, we just add actual component, composition component inside of activity. So activity is activity coefficient times mole fraction, and activity coefficient is changing depending on the temperature and the composition, because activity coefficient is representing the interaction of your species with the surrounding other species in the system, in the solution. Okay? And then very special case. So one case is dilute solution and the one case is very enriched solution. So when your component I in the solution is dilute component, then we can apply the so-called Henry's law. And according to the Henry's law, activity coefficient of species is constant. It's not changing with the composition. It is constant at the given temperature. However, activity coefficient, Henryan activity coefficient, so-called gamma I naught, can be still function of temperature. It can change with the temperature, but not by the composition. That's the Henry's law, okay, Henryan activity coefficient. And then when your solution, when you actually the component is now solvent of the solution, so it means you actually, the solution is mainly composed of the your species now. In that case, the activity coefficient of that component is nearly 1. It's 1 actually, and that we call it Raoultian solution and Raoult's law. Okay, so that we have done. And this kind of Henryan activity coefficient is very important actually, for the, especially for the defining of the metals, or when you deal with actually the impurity element in the solution. All these impurity elements follow the Henry's law. Okay, so it's very important in the many metallurgical processes and also like ceramic processes. And then we try to actually expand those kinds of solution thermodynamics a little bit further to the ideal solution and the regular solution and the real solution. So ideal solution is assuming that activity coefficient is 1. So activity coefficient is not changing with the composition or temperature. It's always 1. So it means when you're actually adding the new component in the solution, in the given solution, that component almost have no interaction with the existing actually the component in the solution. Then there's no interaction, so the evaporation, the pressure which develop by the your given amount of solution is linearly increasing with the amount of the species in the solution. So that's the activity, partial pressure over the partial pressure for the reference state, and that's changing linearly because there's no interaction of the species by the actual other component in the solution. That's a regular solution. And then we derived also the other very extreme case called the regular solution. So when it's the regular solution, there's interaction between the now species, but those interaction between the species only contribute from the enthalpy. There's no entropy actual contribution, but by the interaction between A and B species in the solution, it actually generates enthalpy of the solution, and that could be negative or positive, and that actually excess enthalpy term, enthalpy of mixing term, is expressed by the omega XA, XB, and whereas the omega is the constant term. It's independent of composition, independent of temperature. Okay? And that omega XA, XB is excess parameter, or Gibbs energy, Gibbs excess of the solution, or enthalpy, excess of enthalpy of mixing, or enthalpy of solution. It's the same thing, because there's no entropic term in the regular solution parameter. Okay? So that's what we have learned. But in the real world, when you deal with most of the real solution, this regular solution parameter is not enough. So we need much more parameter than the one regular solution parameter. And then also we need not only with the composition, also with the temperature as well. Okay? So the G excess parameter is really the function of the composition as well as temperature. And to find out those kinds of the excess parameter is one of big deal in the thermodynamic world. So many people actually doing the experiment to find out how does those excess parameter is changing with the composition and temperature. Once you know that, you back calculate your activity coefficient. So if you know the activity coefficient, you can calculate the mole fraction when it has some kind of chemical equilibrium. Okay? You good? That's more or less what we have learned so far. Okay, now we'll move to the phase diagram. So when you're actually going to the phase diagram, we are going to now use the more graphic, because all we have learned so far is mathematical calculation, yeah? Concept plus calculation. But now concept and the calculation is is now represented by the diagram. That's the phase diagram. Okay? So, we can now use this one. How can I put the screen here in the center? Let me ask you. Can I put the screen in the middle? So can you put the screen here? Yeah. He don't know how to do it because we never try. I know. So it should be. There should be some projector. I don't know. Okay. Never mind. Okay, let's look at this one. Okay. So when I actually when I give the presentation in the industry, I always use this kind of slide. Or when I give the actual presentation to the graduate student about thermodynamics, I always use this actually the map. So phase diagram is like this kind of map. Okay. So I mean, as you know, this is one of the treasure map from the Pirate of the Caribbean Bay, the movie. And so if you have this kind of the map and the compass, then you can find, and then you know where you are, and then you know where you have to go, then actually by using this map, you can actually go to the final location as fast as possible without any problem. Yeah. So that's why it's treasure map. And this treasure map is composed by the two components. So x-axis, longitude, y-axis, latitude. Yeah. So you need a location, x, y-axis. And then in the middle, you have kind of obstacle sometimes. So in the phase diagram, you can assume that this is the phase. So which phase I want to have? I don't want to have this phase. I want to have the other phase. Okay. And then in the phase diagram, x-axis, instead of longitude, typically we are using composition. And y-axis, latitude, we are using temperature. So when you have the given AB material, so let's assume we have only AB binary system. When you're mixing, so I want to have final product which have this mechanical property, or this electrical property, or this magnetic property. Okay? Then you have to know first, okay, what kind of phase will make that kind of final, property I want to actually produce. So is it should be FCC, or it should be BCC, or it should be mixture of FCC, BCC, or some other phase. Okay, that's your decision. This is knowledge you need. And then if you have the phase diagram, then you can see where's those area which you want to actually make. So which composition and which temperature you can produce those kind of specific amount of the different phase. Okay? So by using phase diagram, you can find composition and the temperature. So composition is less P, which you are adding in the beginning, and not less P, it's ingredient, how much ingredient you have to put. And then temperature is basically processing time. So the real cooking time and cooking hour, or cooking temperature and cooking hour. Okay? So if you know this one, phase diagram, you can actually you can really develop the material you want to actually have. So many people produced phase diagram. So many binary system, so phase diagram for the binary system have been investigated in the beginning of the 19th or 18th or 20th century, and then a lot of them is already actually investigated. Okay? So most of the common material we are using in the world right now, most of those binary system is already investigated. Okay, for the most of the common material we are using. So most of the steel alloys, we know all the binary phase diagram. Okay? But when you actually go to the more and more advanced material in this day, the phase diagram of those advanced materials is not existing at all. Because measuring one map taking a lot of time, a lot of money. And it's very tedious work. And so nobody wants to do it anymore. And nobody wants to fund it anymore. Unless this is very necessary for their their product processing. Otherwise, nobody really pay this kind of thing. And that's actually what I'm doing. That's my research area. So luckily, nobody doing it, so I can actually attract most of this money and then do it by myself. Okay. So what we are going to learn actually in this class is mainly this one. So a lot of people thought phase diagram is phase diagram, it's map. But however, the phase diagram is graphical representation of Gibbs energy. Okay? So I want to really show you the relationship between the Gibbs energy and the phase diagram. So my research is mainly finding out Gibbs energy function from the phase diagram, and then from all this thermodynamic enthalpy of mixing or activity and etc. All those things eventually will give you the Gibbs energy of solution. Yeah? So all this value will give you this one. Once I know this one, I can back calculate all this one. And then same thing for the phase diagram. Okay? The one-to-one relationship between the Gibbs energy and the phase diagram. Okay, we're going to learn a lot of this one. And some of the actually fast exam, I always ask this kind of question, okay? So when you have this kind of phase diagram, what is the regular solution parameter of the liquid phase or solid phase? You have to expect this kind of actual question for your final exam, okay? Okay. I think all of you already learned phase diagram, simple phase diagram in the introduction course for the material engineering, yeah? So I know you more or less know the terminology of the phase diagram. Okay, let's check. You say, I know, okay. So, when you have this kind of binary phase diagram, let's try to read the first phase diagram, okay? When you read the phase diagram, you have to always read x and y-axis, of course. So x-axis is the composition, y-axis is temperature, yeah? Okay, so when you have this kind of the binary phase diagram, okay, so, and this is the mole fraction of B in this direction, okay, so when I have 70% of A, 20%, 30% of B, where's the composition, axis? 70% of the A, 20% of B. This should be on this side, or this should be on this side? So, it should be in this side. It should be this side. Yeah, good. I asked this question to all the graduate students this year. Half of them fail already. They don't know how to read the x-axis. I was really surprised. So when you have 70% of A, you are talking about this side here, and 30% of B here. Okay. And then you have to now read the temperature. Okay. So let's say my temperature is somewhere here. Then I have this composition and my temperature is this one. And then you have to read what it's saying in the map. Okay? And if you have the very generous map, you have you have the notation for what kind of phase is existing in each area. But sometimes it doesn't give those full notation for each area. Then you have to understand also how to predict what's actually the phase actually in some of the missing area too. Okay, so we're going to learn all this one over the next couple of weeks, or next 2 weeks probably. So according to this phase diagram, okay, so let's go back again. When you have the pure A is here, and this one is say that homogeneous solid solution, and this is homogeneous liquid solution, yeah? So it means this should be the melting temperature of the pure A. Is it okay? And then same thing for this one, and this is solid, this is liquid, so this is the melting temperature of the B. So I know two components which make the melting temperature of the two components which make this binary phase diagram. Okay. And then when you say homogeneous solid solution, so let's assume this is FCC solid solution. Okay. So you have A, B make a completely one solution, FCC ideal solution, for example, and then A, B also make ideal liquid solution as well. Okay, then you can have this kind of phase diagram. And here, so for example, if I have 50% of A and B, if I mix it together at this temperature, then it means, according to this map, it says homogeneous solid solution. So you have one single FCC phase. But it's not pure, it's a solution FCC phase. So Gibbs energy of solution FCC equal to partial Gibbs energy of A, XA, partial Gibbs energy of B, XB. It's ideal, then it means all this RT lone activity is 1 basically. Yeah? There's no term in this one. And then now, let's look at this one. So this one is liquid phase, yeah, on this temperature. And then in the middle here, so let's look at this one. So this is liquid phase. If I cool it down, cool it down, cool it down, now when you meet this one, there's another boundary. And that boundary is connected from here to here, yeah. And then according to this map, all above this red line, everything is liquid phase. Only liquid phase. Single liquid phase. And then if you look at this diagram, all below blue line is single solid solution phase. Single solid phase basically. And in the middle, it means we should have two phase. We cannot say that we should have two phase, but according to the phase diagram, we're going to learn this one later, we have a two phase here. Okay? Whenever you read the phase diagram follow the thermodynamic. Okay? Whenever I say thermodynamic, when you have chemical reaction, you have to consider at the given temperature. So thermodynamic equilibrium means at the given temperature. That's the first condition. At the given temperature, you have something and something. Make chemical reaction, make something. Okay? So when you read the phase diagram, if you know the composition, the next thing is you have to really read at the given temperature. At the given temperature. So for example, this is liquid solution, this is solid solution. When you have this kind of composition here, and when you read the phase diagram, you have to read left side at the given temperature. So you have to read the given temperature. So if this is my composition, you have to read it at this given temperature, okay? So when you actually try to read that, you see that left side there's one boundary, right side there's another boundary, okay? So at the given parallel temperature, at the given composition, you have to read the left side and right side, okay? And typically when you have two phase, that two phase is composed of the one on the left side and one on the right side at the given temperature, okay? So in this case, on the left side, you have liquid phase. On the right side, you have solid phase. So you are, the phase, you have it here, is you have two phase. However, the two phase is, one is from this one, the other one is from this one. Okay? I'll show you why actually the map is like this in the next slide, then you will really understand how to read this phase diagram. But anyway, so we have more simple phase diagram like this, and you have single phase, single phase. Between the single phase, you always have two phase. Okay? And when you have this kind of red line, which show you the boundary of liquid, so 100% of liquid, we call this one liquidus line. So let's look at two terminology. So liquidus is above this means it's above this temperature, above this line of temperature, we have 100% liquid. Then we call that boundary as a liquidus. Okay? And solidus is it should be 100% solid or solids, whatever. Okay? You can have more than one solid. Okay? Then we call this one solidus. And in Korean word, because I mean, you might need actually some terminology in Korean, we call this one called X상선, and this one as 고상선. Okay? Okay? So this red line, so look at this. At the given composition, above this line, everything is liquid. So this red line is liquidous line. And below this one, everything is solid. So this blue line is solidus line. Okay? So in this case, it's very simple, solidus and liquidus. But in some cases, it's a little bit complex. Okay? I'll explain this one. And then, now, let's look at this definition again. What is a phase? So when we say phase diagram, what's the phase means really? Okay? And this was actually very confusing for me when I actually first learned the phase diagram. So typically, the phase is the thing which have the same crystal structure. Okay? So when you have single phase, when you have FCC phase, it means I have FCC crystal structure. Yeah. So it's depending on the crystal structure. But unfortunately, for the gas phase, there's no crystal structure. Yeah. It's gas. So gas, look at the gas. Mixture of all the different kinds of gas can be mixed together. There's no way to dissociate two different gas in the gas state. When you actually dissociate it, it is going to associate again, make one solution again. Yeah. Because the ideal entropy term. The gas always want to be mixed together. So there's only one phase all the time for the gas phase. Okay? When you have system, given system, you cannot say that there's one gas phase, another gas phase. It should be always one. There's no way to split it as two different composition. Okay? So it's one gas phase. Liquid. Looks like most of the time, liquid also doesn't have a crystal structure. But it's not the gas. At least we know that this is not gas. Okay? But however, for the liquid phase, most of the time we have a single liquid phase. Okay? But some cases, liquid and liquid is not mixing together. So you have sometimes two liquid phase at the given system too. And one of good example is oil and water. So oil is liquid, water is liquid, but they are not really completely mixing. Yeah? You have oil layer and the liquid layer, water layer. Yeah? And even for the metallic system, we have liquid metal A, liquid metal B is splitting sometime at a certain given composition and temperature. So liquid is not only one phase, it could have two phases. Same crystal structure, but different composition is forming. Then even in this case, we say that eventually when you increase the temperature very, very high, it becomes one solution, one phase, but at the given temperature, you have two different liquid phases. Okay? And then solid solution. Solid. We have many different solids because we have FCC, BCC, and then there's so many different, the crystal structure. But FCC, BCC is a very primitive way we actually define the crystal structure. But you learn probably crystallography course and say that we have the Bravas lattice and we have the prototype like 250 some blah, blah, blah. And that even is not enough to actually define the crystal structure. So we're really going to what's the prototype, what's symmetry and the prototype. When all this one is matching together, we call that as one single crystal phase. But if this is different, we have two different crystals. Okay? So we have so many different kinds of solid phase. So if you look at this kind of example, let's count how many phases we have in each system. So very first one, we have liquid aluminum magnesium phase, yeah? And then we have HCP solid aluminum magnesium phase. So in the given system, we have two phase. Am I right? Two phase. And then for the second case, how many phases do we have? One, two, three phases, yeah? We have gas phase, slag phase, and then liquid still phase. Three phase. And now, let's go to the third, getting more complex. Third one. How many phases do we have? 1, 2, 3, 4, 5. Do we have 4 or 5? 4. How many? 5. You are very wrong. You see, there's the FCC solid phase. It's physically apart each other, but it's the same phase. Okay? So physical separation doesn't count actually phase. Okay? So you could have, for example, at the given system here, I have ion in that corner, ion in this corner. But within the system, these two ions should be the same ion. The amount may be different in each side, but chemical composition and temperature should be same. Because the same phase. Okay? So when you count the phase, it's not physical separation. This is one of the things I was very confused when I actually learned the thermodynamics. Why? I mean, these two different. So it should be independent each other, but it's not independent. According to thermodynamic rule, it's dependent. So FCC solution, FCC solid phase, BC solid phase, liquid and gas. Okay, 4. And how about the last one? This is 5, yeah. I mean, you have gas phase, FCC solid phase, Mg17Al12 phase, and then Al11Mn4 phase, Mg2Si phase, yeah. All this one is different. Different stoichiometry can tell that this is different crystal structure, first of all. If you have same crystal structure, typically the ratio should be same, at least. Otherwise, it's a different crystal. Okay, now let's look at this one as the last example today. So when you have this kind of phase diagram, I mean, if you look at the Gibbs energy diagram, then it looks like this. So this is at when the temperature is T1 temperature. When the temperature is T1, so you can actually see this part here too. Can you see it? It's too far, yeah? When it is T1, so this temperature, okay? The Gibbs energy, if you draw the Gibbs energy diagram, it looks like this. Okay? So x-axis is same composition, but y-axis is Gibbs energy at the T1 temperature. So I'm drawing only T1 temperature, Gibbs energy. And when you draw the T1 Gibbs energy temperature, you have, for example, when you look at the A, from the A point of view, pure A point of view, A is in the liquid state, yeah? And from the B point of view, B is solid state. Okay? So, for the A point of view, Gibbs energy of the A liquid should be lower than Gibbs energy of the A solid. Am I right? So, I know at least 2 points. I don't know where exactly, but however, I know that liquid should be lower than solid Gibbs energy. Just whenever you have low Gibbs energy, it's a more stable state, yeah? So energetically, when you have low Gibbs energy, it means more stable stage. Okay. And in case of solid, you have B solid should be lower than B liquid phase. Is it good? And then we assume that there's FCC solution and then liquid solution. So there's 2 solution phase. And we have learned all this Gibbs energy. When you actually learn the Gibbs energy of solution, FCC or liquid, it should have continuous function from A to the B. Am I right? By some sort of whatever excess parameter, but you should have some continuous function. So A should be connected to the, A liquid should be connected to the B liquid. And then A solid FCC should be connected to the B solid FCC. We don't know exactly what's the shape, but if you assume the shape is like this, it's, most of the time we have negative shape, first of all. And if you have this kind of shape, then according to this diagram, according to this actually Gibbs energy diagram, now we can actually start to reading what kind of phase can be exist at each composition. Okay? At this composition, XB at this composition. Liquid have lower Gibbs energy than the solid. So liquid should be stable phase. Am I right? Because at the given temperature, at the given composition, now what phase have lowest Gibbs energy? That's actually stable phase. Liquid have lower Gibbs energy than solid. And this side, solid have lower Gibbs energy than the liquid phase. Okay? So we know that liquid and the solid is existing in this side and this side. Okay? How about in the middle? This is actually big problem. So let's look at this one a little bit more carefully. So when you have AB again, so this is GB solid. So, I mean, one of the way you can think of it, so this is liquid, this is solid, okay? One of the way you can think about this, okay, below this composition, okay, liquid have lower Gibbs energy than solid. So it looks like liquid and the solid phase existing in this way. So you have to, at the given temperature, T is constant, and then at the given composition, you have to read now which phase have low Gibbs energy, okay? That's how we are reading here. And so here, below this one, liquid is lower, and above this one is solid is lower. So we assume in this way. But however, this is not 100% correct. Because this assumption, I mean, the assumption I made here is there's only single phase. So what is single phase which have lower energy? Okay, liquid and solid. I don't assume there's the two solid phase or liquid phase can exist together. But as you see in the binary system, we can have two solid and liquid phase can exist together, yeah? So if you actually, if you allow that actually two-phase equilibrium, so we can have even two-phase can be stable phase, then the story is different. So if you draw the tangent line between these two curves, so inside of this tangent line, okay? If I have a single phase, for example, at this composition, let's take this composition. If I have single phase of solid have this one. If I have single phase of liquid, this one. But if I'm allowing solid and liquid can exist together, then it means at this composition, I can split my system, my composition, this plus this two phase. So I have this fraction was, so I have actually this fraction of this phase and this fraction of this phase, then I can make this composition. And then the sum of these two Gibbs energy should be lying on this tangent line. So this Gibbs energy is lower than even pure liquid or pure solid. Single solid or single liquid phase. Okay? So the mixture of liquid plus solid, so the mixture in this case, liquid plus solid, is more stable than just solid or just liquid phase. Okay? So when you have any kind of Gibbs energy curve, it's determined at the given temperature. Okay? You have to draw the tangent line between the different phases, and that tangent line typically give low Gibbs energy than the pure single phase, so solid or liquid phase. So, because we want to find what's the minimum energy state. I don't care whether it's only single phase or two phase. Okay? So if you allow the final equilibrium state, this summation of the two solid and liquid is lower, have lower Gibbs energy than the pure liquid phase or single liquid phase or single solid phase. So inside of this tie line point, or inside this two tangent line, cotangent line point, we have two phase. And then outside is liquid and outside the solid. And you might say that, okay, then why, I mean, this, if I connect this one, you even have lower Gibbs energy as a solid plus liquid than the liquid. But outside here, at this composition, you cannot make, by combining these two compositions, you cannot make this one. Because this one have 30% of B, this one of B, and this is only 10% of B. Yeah? So cotangent line is not existing outside of your cotangent point. Okay? So within the cotangent point, you can check whether your two mixture is lower, have a lower Gibbs energy than the other. But outside that, you cannot really tell. You cannot apply because it's mass balance problem already. Okay? So according to this phase diagram, we'll have at this temperature, up to this composition, we'll have liquid phase, this solid phase between these two, liquid plus solid. That is actually reflected. So these 2 points here is corresponding to these 2 points here at this diagram here. That's why that actually solidus line, liquidus line is existing there. And then if you change this one, if you draw this kind of diagram continuously with a different temperature, you can find all these 2 points at the given temperature. And then if you're connecting them, you can make this kind of phase diagram. Okay? We'll continue this one, and then in the next about 3-4 lecture, I'm drawing this kind of diagram and explain case by case how this Gibbs energy looks like, and then based on this Gibbs energy, how the phase diagram looks like too. Okay? So don't worry, we'll come back again this one next week. Good.